So projection of a vector A onto a vector B. Now I'll draw a little diagram, a little start diagram here. Here you see a vector A, and what we're going to do is we're going to project it onto vector B. I've drawn two diagrams, so just to show you what happens when vector A and A is the same, but B is shorter and longer. It doesn't make any difference, in fact. The projection is the same. And the way we're going to look at this, I'm going to think about the sun. So let's draw a sun. The sun is up here. And the sun shines. It's so high up for us that all the rays of the sun come down pretty much parallel. So there's going to be a nice shadow. Right? That's the same for the other diagram as well. So we'll find ourselves a nice little shadow. That's a right angle there. And you'll get a nice shadow coming across here. That is the projection. That is the projection of A on B, or onto B. And in that other diagram, the sun shines there as well. Same deal. A at A hasn't changed, so that shadow is going to be exactly the same. Think of that bottom part being the ground. So that's exactly the same thing. So it doesn't matter about the length of B. The projection, B is just the direction of the vector, and you're projecting A onto that direction, and that's the part that gives you the size of A. So that's the projection of A onto B with vectors. So how do we actually find that? Well, there is a formula. We won't go into proving the formula. I think we'll just talk about the formula. And the formula is this. The projection, it's a special notation, proj A onto B. And the formula is like this. A dot B, we'll define that in 2 seconds, divided by the magnitude of B squared, we'll define that as well, in the direction of B. Simple. And A dot B, assume A is A1, A2. I write vectors vertically like this, except that was pretty bad. Let's rewrite that bracket. Dot B1, B2, B3. And the dot product is just a matter of multiplying these guys along here. So you'll get A1 times B1 plus A2 times B2 plus A3 times B3. And the other one, B, that's my notation for the magnitude of the vector B, which is the square root of B1 squared plus B2 squared plus B3 squared. So that means that B squared is just going to be the sum, because you get rid of the square root when you square it. And that's all there is to it. That's how you use that formula. But let's see it in action with some actual numbers, okay? So just some action here. And we can do this in R2 or R3. An example in R2 would probably be very nice, I think. Example in R2. So let's, in other words, an X and Y axis, let's draw something like this. I'm just making this up as I go. If we take 1, 2, 3, 1, 2, 3, 4, 5. Okay. I'm going to take a point there and a point there. So that's the point 3, 3. and that's the point 1, 1. So that means this vector here, which can be our A is going to be 2, 2. You just go 3 minus 1. That tells you how much in each direction you're going. That's the vector A. Vector B, let's draw that different color for that one. Let's let that be vector B. That's the point 4, 1. So B is 4 minus 1 is 3 and 0. So it points 3 to the right. That's the length of B as well, which is going to be handy for our formula. So then let's apply the formula then. So the projection of A onto B, you can see it here. If I drop the perpendicular, it's going to be that blue vector right there. So I already know the answer is 2, 0. So let's apply that and see. Equals, let's just get some more space on that. Equals, so A is 2, 2, dot it with B, which is 3, 0, over B is 3 squared plus 0 squared, square rooted and squared, and it's in the direction of B. Equals, it's 2 times 3, because that's the dot product, plus 2 times 0, over 9 in the direction 3, 0. Let's work that out. That's a 6 over 9. That's 2 over 3, 3, 0, equals, and you multiply in, so that's 2, 0 as promised. There you go. Does that make sense? So that was an example.